All right, everybody, welcome back to Calculus 3. Today we're going to do lecture 13, which is talking about tangent planes and linear approximations. Now, this may seem familiar. You may in Calc 1 remember tangent lines and linear approximations, and it turns out that that's going to be essentially what's going on here. Let's see here. Just actually, let me pause the recording. All right, sorry about the interruption. We're trying to get the audio working all right here. Anyways, so yeah, like I was saying, this section of Calculus 3 is extremely similar to the corresponding section in Calculus 1, where we used the tangent line to approximate the value of a function. Like say, for example, this is some kind of bizarre function that we may have a hard time working with, and we want to know, say, its value right here. Well, rather than actually plugging in that value into that function, which can be kind of difficult, like for example, doing the square root of like 9.01 or something, that's kind of hard to do like on its own. But what we could do is we could approximate it by following the tangent line instead. So what we're going to be doing today is we're going to approximate the value of certain points on surfaces by following the tangent plane. So we're essentially just kind of stepping up a dimension here of what we did in Calculus 1. All right, so let's see here. Let's start off by talking about differentiability and tangent planes. So let's see here. We would like to say that a continuous function is differentiable if it's locally linear. And locally linear in our case is going to mean it has a tangent plane. So if we're able to make a tangent plane to a function somewhere, then we're going to say it's differentiable. Now, there's a more technical version of differentiability, but we're not really going to deal with that because that has a lot of epsilons and deltas and also some linear algebra baked in there too. So we're not going to do the rigorous definition, but we're going to say something's differentiable if it's locally linear, meaning it has. You could approximate it with a tangent plane. All right. So let's see here. How we're going to define this tangent plane, we're going to do this equation right here. Z minus f of a b. So this, you can imagine this being like z naught. And then we have the partial derivative with respect to x, and then we do x minus a, the partial derivative with respect to y, and then we do y minus b. And this we can imagine as delta x, and this we can imagine as delta y. So a more familiar version of this would be the Calc 1 version, where we had y minus f of a is equal to f prime of a times x minus a. All we're doing here is we're just adding in a different direction that we can go in. So we have both of our partial derivatives indicating we can move not only just in one direction now, but in the x or the y direction right here. So this is the Calc 1 version, and this is our new Calc 3 version, now that we know what a partial derivative is. All right. Let's see here. Let's talk a little bit more about this. So suppose we have a function that's defined near a point, and let's suppose that both of our partial derivatives at that point exist. We say that f is differentiable if it is locally linear, meaning it has a tangent plane right there. It can be approximated with a tangent plane. And in this case, the equation of the tangent plane is what it was on the previous page. This is the same equation that we had on the previous page right here. It's just with f of ab moved over here. Point AB is where we got the tangent line, right? Or yeah, in this case, the tangent plane. We're finding the tangent plane at the input point A and B. Because remember, now we have two different input values here. All right, another way to imagine the tangent plane is that it's the unique plane containing the tangent lines to the two vertical traces through P. So let's say we plug in x equals a. So x equals a will be this plane.
Professor, can you please go up?
Sorry,
thank you.
All right. One more. There we go. So let's say we're at x equals a, right? If we plug x equals a into this equation right here, what's going to happen? Well, we have z is f of AB. If I put a into here, this is going to be 0. So we don't really have this part anymore. But we do have partial f partial y, y minus b. And then if I subtract this, this might look a little bit familiar. This is essentially the Calc 1 tangent line, only we're doing it in a particular x value, so we have y and z values that we're allowed to do here. And in the same way, if I stopped and looked at the y equals b plane, actually, let me draw the picture of this. So here we're getting a Calc 1 tangent line. How is that looking? So there's our curve that's in this plane. This is the intersection between the plane and this bendy curve. And then we have our tangent line like that. And if we do y equals b, we can get something similar, only this time it's going to be going this way instead. So it's going to be going y equals a value. That's not very good. Let's see. There we go. A little bit better. Yeah, so this would be the tangent plane, or sorry, just the plane y equals b. And if we drew a picture in there, we would have the line of intersection between our plane and our curve, or our surface right here. And then we have the tangent line for that. So the tangent plane is the unique plane that makes us have both of the 1D tangent lines in each direction right here. Can I zoom my screen a little bit? Yeah, sure. Does this mean we can write planes as 2 lines and not a normal vector or a point? Yeah, you can identify a plane like that. That's kind of the same way we identify a plane by having those 2 vectors. Like, you know, when we have 3 points and then we subtract them to make those 2 vectors. That's kind of similar to this. If you have 2 lines in different directions, but they're both in the same plane, you could identify a plane like that. Can we move the paper to the left a little? I mean, there's nothing really over there. All right. That's kind of the abstract definition of a tangent plane. Loosely speaking, the tangent plane is going to be the plane that it's just going to be the surface that's very close to our surface at a particular point. It kind of just kisses it there, kind of similar to the tangent line. It's kind of hard to see. Yeah, unfortunately, both of my pens ran out of ink at the same time, so I'm relegated to using a pencil today. I apologize for that. Find an equation of the tangent plane to the surface z equals x sine of x plus y at this point right here. All right, so remember our formula for a tangent plane right here. Oh, that's broke. It's going to be f of AB plus partial f partial x, and then we have x minus a, and then we have partial f partial y with y minus b right here. Then what are we supposed to do? How are we supposed to fill this out? Well, let's see here. So our point AB, we have a being -1 and b being 1. And then this means that f of AB is 0. That's like the z value. So what is this guy going to be? This is going to be 0. Now, in order to fill in the rest of this stuff right here, let's see. Well, sorry, I just got distracted for a second. Let's go ahead and see what these partial derivatives are. We need to know what those are. Okay, so let's see, or I should say partial z, partial x. Okay, so if I do the x derivative of this, let's practice doing our partial derivatives here. So let's see, so we have an x here times a sine of something with x right here. This is going to be requiring us to use the product rule. So I'm going to take the derivative of x right here and get 1. And I leave the sine part alone. And then I leave the x alone and take the derivative of sine, which will be cosine. Now the derivative of x plus y with respect to x, that's going to be 1. So I don't really need to do a chain rule here. But anyways, this is going to be my x partial derivative right there. And then let's go ahead and get the y. So partial z partial y. All right, now this time x is a constant. So all I'm really doing is just taking the derivative of sine. So I have x cosine of x plus y. And then the y derivative of this inside right here is going to be 1 again. So this is actually a pretty easy partial derivative right here. We didn't even need to do a product rule for that. Okay, now what we're supposed to do is we're supposed to plug in the point -1, 1, 0 into these, and that's what these are going to be. All right, well, let's see here. So partial z, partial x at -1, 1, 0. Well, let's see here. So if x is -1 and y is 1, this will be 0, and sine of 0 will be 0. Then we have minus cosine of 0, so that will be -1. So this part's going to be -1, and then we have x minus the a value, which is -1. So this is my a, this is partial z, partial x. All right, let's get partial f, partial y now at the particular point. So partial z, partial y, if we plug in -1, 1, I guess I didn't need to put the 0 here because we're just plugging in x and y values for this. So if I plug in -1, 1 into here, I have negative cosine of -1 and 1 and 0 again. So I have -1 for that too. Okay, so both of my partial derivatives here are -1. And then I have y minus b. So I have y minus, and then my b value is 1. All right, so this is partial z, partial y, and then this is my b. All right, so if we write this out in a nicer way, what do we have? We have z is going to be negative x plus 1, and then we have minus y minus 1 right there. And that's a totally acceptable way to write a plane. So we could kind of just leave it like that right there. Why is f of a b 0? Well, remember, f of xy is z, right? Kind of like how f of x used to be y. God, this pencil. Okay, so f of xy is z. So if I plug in -1, 1 into here, I get the z value, which is going to be 0 right there. Can you simplify it? Yeah, you could definitely simplify this. So we have -x minus 1 minus y plus 1, and then those go away. So you could also write this more simply as z is -x minus y, if you'd like. There we go. So we ended up getting our tangent plane right there. All right. So the formal definition of differentiability, like I was saying earlier, ends up being difficult to apply, meaning we're going to have to use deltas and epsilons for all that kind of stuff. If you are interested in that, though, if you're interested in like what's going on under the hood with calculus, I recommend taking advanced calc, but we're not going to be doing that stuff in here. However, there is a way to see if a function is differentiable without having to do deltas and epsilons here. Okay, so here's a theorem. So here's a sufficient condition for differentiability, meaning that if the following conditions are true, then we know we can find a tangent plane for our function. So if we have the partial derivatives fx and fy, so if we take both of our partial derivatives and they exist near a point, and they're also continuous at that point as well, so not just the function, but the partial derivatives are continuous, then we know f is differentiable there, meaning we can get ourselves a tangent plane. All right, so that's kind of our condition here. So we need to see not only that the partial derivatives exist there, you might think that would be enough, like if we can get both of those, but we also need to see if they're continuous. So let's check that for this problem right here. So is the function f of xy with x minus y over x plus y differentiable at the point 1, 1? Well, in order to do that, we need to find both of our partial derivatives and then see if they're continuous at the point 1, 1. How close does it need to be near? To be more specific about that, that would get into the delta epsilon kind of things. It means you effectively can, if this is our plane right here, and this is AB, it means you can draw a circle around AB, and it's going to be continuous all within that circle. If you could draw any circle like that, then it satisfies near. That's what's going on. How big is that circle? It depends on what kind of function it is. Yeah, this is where you're kind of stepping into the advanced calc zone, and you're figuring out, oh, how big is epsilon depending on delta. So again, we're not gonna do that today. That's going to take up way too much time. All right, so let's check to see if this is differentiable here. Let's do partial f, partial x. All right, now in order to do this, we're going to have to awaken our old friend, the quotient rule here. So I'm going to square the bottom. I'm going to square the bottom right there. And then I'm going to bring x plus y up here. And then I'm going to do the x derivative of the top. Now the x derivative of the top is 1. And then we subtract. And then I leave the top alone. And then I take the x derivative of my bottom, which is also 1. Okay, so if I simplify this, I have x minus an x will be 0. And then I have y minus a negative y, giving me 2y over x plus y squared. Okay, now let's see here. So the whole point of this was to see if it's continuous at this point. So is this continuous at 1, 1? Is there any issues with plugging in the point 1, 1? Does everything work normally there? Okay. Yeah, there's no issues there. The only issues we could have with a rational function is dividing by 0, but putting 1 in for both of these will not result in dividing by 0. So we are continuous at 1. If it were like negative 1, 1, that might be an issue. All right, let's check the other partial derivative. We also need that to work nicely there. So we're doing another quotient rule, only we're kind of flipping our perspective and we're considering y as the variable. So we have x plus y squared. All right, we bring the old bottom up. And then we take the derivative of the top. Now this time the derivative of the top is negative 1. Then we subtract. And we have the original top. And we take the derivative of the bottom, which is 1. All right, now if we simplify this right here, I think we're going to end up with negative 2x. Negative 2x over x plus y squared. And just as before, just as this guy up here, are we continuous at 1, 1? Yeah, there's no issue with that. We're continuous at 1, 1? Yes, we are. So since we're continuous with both of our partial derivatives at that point, then we conclude that f is differentiable at the point 1, 1. And essentially, we would be able to repeat this for any point that doesn't make the denominator be 0 here. If it makes the denominator be 0, then we might have an issue with continuity of our partial. But we know we could find a tangent plane at the point 1, 1 if we wanted to. All right. So let's see here. So this may seem familiar back from Calculus 1. If a function f is differentiable at a point, then it's going to be continuous at a point. So remember, being differentiable is a stronger condition than just being continuous. Because, for example, something like a cusp or kind of a sharp edge right here, this is continuous, but it's not going to be differentiable. And we end up having similar things in higher dimensions as well. Didn't we say that the x and y partials are equal in the last lesson? That's if we do the second derivative. So if we do one of each derivative, then those are going to be equal so long as we have the continuity there. All right. Now, one way to interpret this that's probably even more common to think about it this way is that not continuous implies not differentiable. So if you see a function that isn't continuous somewhere, you immediately know that it's not going to be differentiable, and you shouldn't even bother trying to find a tangent plane. All right. So let's see here. So let's suppose we have f of xy being this kind of strange function right here. And we know something fishy is going to happen when we have one of these piecewise functions here. Usually we get some pretty contrived examples when those show up. So this is going to be this rational function everywhere except for 0, 0, which would make the denominator 0. And essentially we're trying to plug in that hole by saying that once we get to the origin, it's just going to be defined to be 0 right here. All right, so what we're going to do is we're going to show that f is not continuous at 0, 0. All right, so I think this was a few lectures ago. How do we show something is not continuous in this class? What was our method of doing that? Yeah, so we look at a limit, right? And we want to show that the limit doesn't exist. Now, how did we show that the limit doesn't exist in the past lessons? Let's see. I think Jenna has it here. We look at the limit on different paths right here. So what we do is we approach the origin or the point where we could possibly not be continuous. We approach it in different ways along different paths. And if we get a different value depending on which path we take, then that means it's not going to be continuous there. Okay, so my first path here, and there are a bunch of ways to do this, by the way. You don't have to do these two specific paths. These are the first ones I've kind of thought of. Why don't we try along the path y equals x? So our original limit is the limit as xy goes to 0, 0 of xy squared over x squared plus y to the fourth. All right, so this is our limit that we're doing. Now, if we move along the path y equals x, what I'm going to do is I'm going to replace all of these y's with x's, because x equals y on this path. So now, oh my God, now we only have x going to 0. And I have an x times x squared over x squared plus x to the fourth. Now let's see here. I can divide out an x squared between each of these right here. That goes into all of the terms at least once. So I'm going to be left with an x up here, a 1 down here, and an x squared right there. Okay, and then this limit, this is a limit where we could just straight up plug in 0 right here. If we do that, we're going to end up getting 0. Now, if this is continuous, that means that no matter what path I took, not just y equals x, but any path, should be exactly the same. But let's try a different path. Let's see if it keeps working that way. I'm going to try the path x equals y squared. And this one I didn't entirely pick randomly. I picked this one because it would make the bottom here have the same degree between both of these. So if I pick x as y squared, then I'm going to get another y to the fourth here. So if you can pick something, a path that makes that happen, then that's usually a good idea. You might get some different behavior from other paths. All right, so let's do our limit again. Let's see if we get the same thing. So we have xy squared, x squared plus y to the fourth. All right, so now I'm going to replace all of these x's with y squared. And I'm going to have y go to 0. So I have y squared times y squared over y to the fourth plus y to the fourth. All right, so let's see here. Every single term we have is a y to the fourth. So we could divide all of it out. And we end up with a 1 over 1 plus 1, aka 1/2. But unless we're working in a degenerate mathematical world, 1/2 is not equal to 0 right here. That means that we were able to follow two different paths and we were able to get two different answers, meaning that it is not continuous right here. We are not continuous at 0, 0, which means also that we're not differentiable there either. So that means that we can't have a well-defined tangent plane there at that point. So not differentiable there, no tangent plane. Okay, so there we go. So the function is not continuous, meaning it's not differentiable there. Now I want to show you guys something that's really weird for our next part. So I'm going to show you something that's a little bit weird and counterintuitive, but I'm going to show you a picture that will make this make sense right here. Do we make it y squared so the bottom would add? That's right. So if you pick a path where the bottom and also the top too, if you're lucky, is all the same degree, that's a good path to pick. That often leads to either counterexamples or seeing that everything's the same. So that's a good path to pick. I usually try to pick that one when I can. All right. So next, let's take a look at the same function. So this is the same function that we had before. Now what I want to do is I want to show that f of x at 0, 0 and f of y at 0, 0 exist. This is my next goal right here. Okay, so let's see. Now remember, the partial derivative at AB is the limit as h goes to 0 of f of a plus h and then b minus f of ab divided by h. All right, well, in our particular case, we want to know what's happening at 0, 0, right? So let's see here. We have the limit as h goes to 0 of f of h0 minus f of 0, 0 divided by h. Okay, so let's see what this limit is going to give us. And we need to do a limit definition of the derivative here because we have this piecewise thing going on. So whenever we have a piecewise function we're trying to do the derivative of, we need to go back to the limit definition. Something weird might happen when we jump between the pieces here. Let's see, f of h0. That means that I'm using this definition because I'm not quite at the origin because I have this h here. But I am plugging in 0 for all of the y's. So why don't you guys tell me, what is f of h0 going to equal? What number is that? Anyone see what f of h0 is going to be? It's something pretty simple. It's going to be 0. That's right. Reason being is that this is x and this is y, right? So if I plug in y equals 0 right here, I'm going to have a 0 in the numerator. And then I have h squared plus 0 down here. So I have 0 over h squared. That will be 0. All right, f of 0, 0 is literally defined to be 0. And then we have that over h. So this is the limit as h goes to 0 of 0 over h. That is a big old 0. So that is going to be our partial derivative of x at 0, 0. Try to make them a little bit more defined. Yeah, sorry about that. Let me try that here. There we go. I'll make the legs a little longer. All right, now let's do the same thing for y. All right, so if we use the same definition, we have the limit as h goes to 0 of f of 0 h minus f of 0, 0 divided by h. All right. Now, this time, we have a 0 for x and then an h for y. But it doesn't really matter because we have them multiplied on the top here. So as long as at least one of them is 0, our whole thing is going to be 0. So we end up with 0 for that. This is once again 0, and we have over h. Well, I see some people talking about indeterminates here. So like this might be a 0 over 0 situation here. There's one way we could do this, which is L'Hopital's rule, which will give us 0 over 1, which is definitely 0. But another thing is that if we imagine that h is getting smaller and smaller and smaller, we're doing 0 divided by 0.1, 0 divided by 0.01, 0 divided by 0.001. What are all of those equal to? It's 0. So the pattern here is becoming, it's just 0, 0, 0, 0, 0. So that's the limit. And then so once again, we get 0. Okay, now this is very bizarre. And let me explain why this is a bit bizarre. On the previous page, we just said that f wasn't differentiable at 0, 0, right? What we just got partial derivatives. We just got that our partial derivative of x is 0. We got that our partial derivative of y is 0. These weren't d and e. These were 0. So how do we reconcile this? How could you not be differentiable yet still have partial derivatives? And this does not have an easy analog in calculus. So we are kind of stepping into something new here. So to illustrate this, I want to share with you this picture right here. For the Zoom people, just a moment. Okay, so can everyone see this now? This is the graph of the function that we just took a look at here. And you can see that there's some interesting stuff going on when we get close to 0. It's almost like it's kind of getting pinched together. First of all, I want to go over the different paths. You see this kind of ridge coming up along here where my mouse is moving? This is the path x equals y squared. And as you can see, we're following this path x equals y squared, and we're kind of going up a ramp here, and it's leading us towards 1/2. Whereas on the other hand, if we follow y equals x, we would kind of crash straight into the origin right there. So we could see why it's not going to be continuous right here. But that doesn't explain the mystery with the partial derivatives, though. How does that work out? Well, let's take a look at what happens in the x direction right here. So this red axis, this is the x direction. So if I take a look at what's going on there, you see that as I move here, it's perfectly flat in the x direction, right? So this is why our x partial derivative is 0. Why is it moving on its own? Our x partial derivative is going to be 0 because this is totally flat when we move in the x direction. The same thing happens in the y direction. We're totally flat when we move in the y direction out this way. But why is this not differentiable? Why isn't our tangent plane just z equals 0? Essentially, the function can't decide where to put this tangent plane. So if I were to start writing out the equation of my tangent plane, I would have z is f of a b, that's a b, and then I have my partial derivatives, x minus a, partial f, partial y.
We can't see that.
Oh, yeah, that's right. You guys can't see me now. Let me flip over. Go back to the paper. There we go. All right, so here's our tangent plane. So let's see. So A is 0, we got that. B is 0, we have that because we're looking for the tangent plane at 0, 0. We know that this is 0, and we know that this is 0 because we just found the partial derivatives, right? They're both 0. So this is a variable. This is okay. We want some kind of variable in our plane equation. That means that this is the issue right here. This is the problem. Because maybe our tangent plane could be z equals 1/2. That would agree very nicely with what we saw going up that ramp over here. That would make sense as a tangent plane there. But on the other hand, what about z equals 0? That would make sense if we went along the path y equals x. So the reason why we can't have a tangent plane here is it's not that it can't decide which way it wants the tangent plane to be, it just can't decide where it wants to put the tangent plane, whether it wants to be at 0 or it wants to be at 1/2. And you can actually rig this path, like depending on which path you go down, you can rig it to be any number between negative and 1/2 and 1/2. So how do we know where to put the tangent plane? And there is no good answer to that. So that's why this is not differentiable right here. Yeah, you can rig it to be anything you want between those numbers. That's why these things are simultaneously able to be true. Both of the partial derivatives could exist, but f is not differentiable, meaning that f doesn't have a well-defined tangent plane right here. All right. Moving on from that, what do we do with these tangent planes if we do have them? What's the point of this? Well, what was the point of tangent lines back in Calc 1? It's to approximate things. So linear approximations really aren't the best approximations. We learn better approximation techniques in Calc 2 with infinite series, but they often do a pretty good job. So we can use linear approximations to help us approximate different things if our function is a bit awkward right here. Okay, so let's see here. So let's say we have a linear approximation and we want our function to be approximately equal to L. What is L going to be? L is going to be none other than our tangent plane. Kind of like how the linearization back in Calc 1 was none other than the tangent line, the linearization in Calc 3 will be none other than the tangent plane right here. So what is this saying right here? Well, the linearization starts at the same point that the function does at AB. So this is kind of like a reference point. So for example, maybe back in Calc 1, we wanted to approximate the square root of 9.01. What would we use as a reference point in that situation? Yeah, we would use 9, right? Or the square root of 9 or 3. Yes, we use a function value that's nice, that's close by. And then what we do is we have a small change in x, and then we have a small change in y, and we multiply those by the rates of change in those directions. And this will roughly tell us how far off we're going to be. And here's the picture describing this. So the dark shaded area is the surface, and then just below it is going to be this tangent plane right here. So they're going to be exactly equal to each other at the particular point right here. But then as we go further and further away, it does an okay job at approximating maybe around here, but then it gets worse and worse as we go further away. And that's true of any kind of linear approximation. The further away you go, the worse it gets. Why is L equal to this? Well, L stands for linear, and this is the plane created by this linear equation right here. So that's why it's called L. Let's see here. And then, oh yeah, I guess I already wrote this up here. But we could write f of a plus delta x, b plus delta y as f of a, b plus partial f, partial x, delta x, partial f, partial y, delta y. That's pretty much what I wrote up there already. Okay. So why don't we practice this? Why don't we actually do something? So I mentioned square roots, and we can also do square roots using this as well. So find the linear approximation of this function at the point 3, -4, and use it to approximate f of 3.1, -3.95. So this is definitely an awkward number to put into a square root, but maybe we can at least get a good approximation of it using this right here. All right, so first of all, we need to get the linearization, which is f of our AB, which is now -3, -4. Then we need our partials at that point, and then x minus 3. And then we have the y partial plus 4. All right, so let's do our partial derivative of this right here. Let's see. So this is the square root of something. So I know I'm going to do 1 over 2 times the square root of that same stuff. And then I multiply through the chain rule. I multiply by the x derivative of my inside stuff right here, which is 2x. Remember, y squared's derivative is 0 in this case. So we have both of those going away. So I get x over the square root of x squared plus y squared. Now, x and y are very symmetric in this function. If I flipped x and y as variables in here, this would not change at all. So with that in mind, if you just had to guess, what do you think the partial derivative of f with respect to y is? I guess it's kind of hard to type out. Yeah, someone in the audience said it. Yeah, that's right. So it's y over the square root of x squared plus y squared. We're essentially doing the same thing over again, only we're doing it with the y symbol instead of the x symbol. So one thing to watch out for to save time with partial derivatives is symmetry. If you can flip the x and y in your original formula and it won't change anything, then you could flip the x and y in your partial derivative formula and it'll be correct. That's kind of one way to save time. All right, and then at the particular points, let's see, we have 3 over the square root of 9 plus 16. Oh, hey, wait a minute, this is a 3, 4, 5 situation. So this is 25, and then we get 3/5 from this. And then partial f, partial y, it's going to be -4 over the same. So we have -4/5, like this. All right, so that means we're ready to fill in our linearization here. Let's see. Oh, what's f of 3, -4? Well, that would require us to put 3 and -4 into here. So why don't you guys say it? What's f of 3, -4 going to be? It's going to be 5. That's right. We're doing the square root of 9 plus 16 again. All right, so we have partial f, partial x, x minus 3, and then we have -4/5 y plus 4. All right, there we go. So there's our tangent plane, which is also called a linearization. We found that, that's good. All right, and then now's our time to use this. So if we were to put these directly into the function, it'd be 3, 4, 5, and we would get 5 as our answer. So that stands to reason that if we plug in numbers that are kind of close to 3 and -4, we should get a result that's kind of close to 5. That's exactly what's going to happen here. So L of 3.1 and then -3.95 will be 5 plus 3/5, and then we have 3.1. Oh my God, 3.1 minus 3 minus 4/5, and then we have -3.95 plus 4 right here. So this is 5 plus 3/5 times 0.1 minus 4/5 times 0.05. I didn't need this parenthesis. Okay, and then now we're verging into calculator territory here. So I'm just going to leave this like that there. I guess we could figure out exactly what fraction it is, but yeah, that's not really necessary. Oh, it comes out to 5.1, really? Exactly? Oh, so it's a positive change, 5.016. The one in the audience. Oh, 0.02. Oh, I guess that's rounding. Okay, well, it's really close to 5. That's the moral of the story. Close to 5, because these numbers are close to 3 and -4, respectively. How are we doing on time here? We doing good? All right, wonderful. All right. The linear approximation is often expressed in forms of differentials. So a little bit of change in f is going to be the partial derivative of f with respect to x times a little bit of change in x, which will be dx. And then we have that we could also change f in the y direction. So we have partial f, partial y, dy. This actually has a special name. This is called the total differential. And I strongly encourage you guys to remember this. This is going to be sort of the basis for our foray into the chain rule, which we're going to talk about next time. So this is what we're going to be dealing with next time. So make sure you remember the total differential. I don't know why this was in the notes twice. Oh, yeah, sorry. This is supposed to be df plus f of ab. So if you start wherever you started and then you do a little bit of change in f, then you're going to get this right here. All right, so then it has another linear approximation problem here. So find the exact change in the function and the approximate change in the function as x changes from 2 to 2.05 and y changes from 3 to 2.96. Okay, so let's do the exact change. Okay, so f of, let's see, it's 2, 3. This is the starting value. Let's see, so we do 2 squared is 4, plus 3 times 2 times 3, minus 3 squared. Let's see, this is 18, minus 9 is 9, plus 4 is 13. All right, so our function value starts out at 13, and then we end up moving to the nearby point, 2.05, 2.96. And I think I did this in a calculator earlier. Let's see, what did that end up being? I think it was 0.6 something. Let's see if I have it written down here. Yeah, it's going to be 13.6449. So the difference between these, so delta f will be 0.6449. Okay, now let's see how close the differential gives us to having a change of 0.6449 right here. Okay, so remember df is partial f partial x times our change in x. And then we have partial f partial y times our change in y. Well, I guess I'll write d's for this to be consistent. dx dy, which should be consistent with the differential notation. All right, so let's see. Let's do our partial derivative of f with respect to x. We need to do that. Thankfully, this is just a polynomial here, so it's not too bad. So we have 2x, and then 3 and y are the constants, so we have plus 3y. Then we have partial f, partial y right here. Let's see. We're going to have 3x minus 2y right there. All right, and then let's plug in our particular numbers, 2 and 3 for x and y. Remember, we always plug in the reference points here. We're not going to plug in 2.05 and 2.96. We're going to plug in 2 and 3. So we're going to have 4 plus 9 is 13. And then we're going to have 6 minus, 6 is 0. So it doesn't seem like there's a lot of change in y going on right here, but there is a lot of change in x. So df will be 13 dx plus 0 dy. All right, well, let's see, what was our change in x here? Well, our change in x was 0.5. We went up by 0.05. So we have 13 times 0.05. That ends up being 0.65. And I would say that's pretty darn close to 0.6449. So as we can see, the linear approximation is not perfect. It's still an approximation, but it can get us pretty darn close to the actual change in our function value, so long as we're willing to be willing to move around close by. All right, let's see here. Don't know if I have enough time to do this one. Let's see here. Well, we've already done a lot of stuff today. What I'm going to do, I'll post the solution to this a little bit later here. All right. Yeah, but essentially this is just another linear approximation problem. It's essentially using the same formula there. All right, guys. Well, that's about it for today here.